Ranjan, come. All right. So good afternoon, everyone, and welcome to today's edition of Wednesday Colloquium. Echo. Hello. Amol, your laptop, maybe you can say leave video, leave audio, click on the microphone symbol. Okay. All right. So today we are trying out yet another format, still experimenting with this colloquium format. So we have, I'll give you a brief context. Amol will provide you sort of a kind of a chronological context for this whole thing. So we will be discussing three mega science visions today. So these mega science vision 2035, this exercise was commissioned by the Office of the Principal Scientific Advisor to the Government of India. The idea was to identify mega science projects, meaning projects that are technologically and scientifically complex, and which also require capital, human resources, and infrastructural resources, which because of which you can't do very many of those. So that was the whole idea. And this was commissioned to be carried out in 5 different disciplines. Amol will have more details on this. Today, we will focus on 3 of the areas, mega science visions in 3 of the areas, which are most relevant to TIFR, namely the high energy physics, nuclear physics, and astronomy and astrophysics. The reports were out earlier this year. So this is the nuclear physics report. You can download all of this from the PSA's webpage. And here is astronomy, astrophysics report. Amol tells me that the high energy physics is not out yet. The hard copy is not out yet, right? Yeah, it's in print, so you'll soon see it. So the format, what we'll do is the following. Amol will start. He'll first talk about the high energy, but then before going into that, he'll provide an overview of this whole exercise. And he'll tell you what this Mega Science Vision 2035 is and what are its aims, etc. And followed by Palit, who will cover the nuclear physics mega science report, and then after which I will cover the astro part. So Amol will speak for 20 minutes roughly, and followed by Palit and I for 15 minutes each, and then we will have more time for discussions. But feel free to stop them in between as well. So let's start with Amol. Amol.
Hello. Yeah. Okay. So as Manoj mentioned, I'll be talking about these 3 documents. This is the cover of high energy physics document. This is nuclear physics, and this is astronomy, astrophysics. So this was an exercise that went on for quite a few years. And I'll tell you exactly how things were done. But finally, the product of that is now available in the form of a sort of semi-approved report on the website and here. And I think everybody is public for everybody. Everybody is welcome to go and have a look at it. Okay. So this talk, compared to other NSF colloquia you have been to, is going to be less science and more policy. Okay, but not my fault. This happened to be the title of a book one of my friends wrote, and this was a book launch in some bookstore. Anyway, so while the pandemic was on and people had nothing to do, in December 2020, the principal scientific advisor at that time was K. Vijayaraghavan, initiated this process of trying to get a vision document exercise in 6 different disciplines. Actually, there were 5 to start with, and one was added later. The 3 relevant to our discussion today are these 3: high energy astroparticle physics, nuclear and plasma physics, astronomy and astrophysics. Apart from that, there's accelerated science and technology, which is also relevant to TIFR's nuclear physics efforts, but slightly disconnected way. This report also is out, by the way. The other 2 reports, one on ecology and environmental science and one on climate research, are yet to be out. They are still in process. So what was done? So the framework was that there would be a drafting group of 4 to 5 people who were kept in charge of actually typing things out on keyboard. But they worked under the guidance of something called working group, which was a group of about 10 to 15 people. When the report was completed, it was shared with a lot of the subject community, from whom we obtained some feedback. And they were also national and international experts who acted as the referee of the report sometime later. So TIFR did have a lot of participation in this. So for example, in high energy and nuclear physics working groups, the then directors of TIFR were the chairs of the working groups. And we had people in drafting groups, and then the other parts of, so this is all the working group, as a members of working group, and also, as a member secretary. Similarly, in nuclear physics document, we had TIFR directors as chairpersons. They were members of the drafting group, some members of the working group, and then members. In astronomy astrophysics, again, we had 2 people who were part of TIFR. So TIFR has given lots of inputs to these things. So what are the modus operandi? I mentioned some of it in the beginning. So working group members were representatives of all the experiments, the major experiments in the country, also from various institutions, universities, and so on. And they collected information from the community about what the community wanted, what their aims would be for the next 10, 15 years or so. Drafting group then prepared a preliminary draft based on these inputs. The draft went back and forth to the working group a few times. Suggestions came from working group members. They were incorporated, and then it was kept open for feedback from the subject community. So we contacted of the order of few hundred to few thousand people from each of these communities who gave us feedback. These feedback were taken into account in written form, and they were discussed, deliberated, and incorporated in a revised version. This version was then sent to these experts, and then we actually had a meeting in which the experts gave their inputs in addition to written referee reports. Then there was a final revision of the draft. It was presented to the PSA in the meeting. Some suggestions came and they were incorporated. So this all thing took of the order of 3 to 4 years and was a long exercise. However, if I understand correctly, at least in most of the subjects, this was the first time that we carried out things at such a level and actually came up with these books. Okay. Caveats. Nothing here is like approved, right? So this is a vision of the scientific community in high energy physics, nuclear physics, and astronomy and astrophysics. It is not approved by funding agencies or the office of PSA. Nobody is giving you any money for this. Okay? So what do we expect? We expect, firstly, that a document will be read by the concerned government agencies. So we know for a fact that these 2 ones which have been printed right now are actually on the desks of people in various funding agencies. Second thing is something that we can hope for. The reports will have some practical suggestions and some radical suggestions, and we hope that some of them are deliberated to and implemented. Okay, some of the suggestions on which we are having discussions today. We had this small informal meeting, and tomorrow morning there'll be a summary session, and of course you are all welcome to come to this session. What was discussed? So we discussed, for example, which science questions are important to pursue collectively. And that's an important word. It's not something that Amol wants to do, or that Sandeep or Manoj want to do individually, but it's something that you really want to do collectively. It's a question that many people want to solve. Next question was, which of these questions can be addressed practically in the next 10 to 15 years? Because the aim was to have a vision for 2035 and not really for 2100. Then what needs to be done to build up infrastructure and ecosystem, because it's supposed to be a very practical vision in which you also suggest for steps in which things to be done. What would facilitate the inception of new mega projects? We try to lay up a very clear path. What spin-offs may be generated, how you can increase interaction in industry, how much human resource and funding needs to be present. But more than that, what you will find in this report is a repository of information about current science projects that Indian scientists are involved in. So if you read nuclear physics report, for example, you will get a clear idea of what nuclear physics is done in the country. And similarly with high energy physics and astronomy, astrophysics. A lot of discussion happened, and while discussing this, we actually introspected a lot about what we have learned over the last many years since independence, what expertise we have gained, and what scale of physics or projects we can implement. So this is a very practical report in that sense. It doesn't say we are going to do everything. Okay, so nuclear physics and high energy physics are kind of topics that are not very well separated, but we made a sort of notional separation. So in high energy physics, we included colloidal physics, astroparticle physics, and these two main topics. Nuclear physics included heavy ion physics, which we call as high energy nuclear physics, including QCD, low energy nuclear physics, which has nuclear structure, and plasma physics. And both of these included dark matter search, neutrino physics, and high performance computation. And the other things that you see here are the projects in which we are currently involved. Okay, so this discussion actually went on sort of in parallel with Okay. So now I'll come to the high energy physics document and tell you what its main features are. So this is the front page, this is the back page, and the quiz for you is figure out what these three things are if you do not know them already. So the topics that are of interest to the community have been divided into two languages. One language is a language of pathways, okay, so which is energy frontier, intensity frontier, cosmic frontier, and theory frontier. Energy frontier means those goals which can be achieved by going to higher and higher energies of collision, like the LHC and beyond. Intensity frontier are experiments which happen at lower energies, but with very high intense beams, for example, flavor physics and neutrino physics. Cosmic frontier is what you get from particles that reach us from the sky, and theory frontier is what happens when you have no data, you calculate something. These are called goals, which is the new language that is started by the so-called P5 commission in the US. This tells you topics about which we learn things. So there's a quantum realm, so learning about quantum nature of the universe, unknown universe, which is the beyond standard model part, and third is new paradigms, which are something that you might not have thought about, because a large part of mega science is to think about what you haven't thought of. Okay. So these topics are the ones that sort of fit within these roles, and these were identified as the major topics in the particular roles and columns. So practically speaking, the pathways by which we do things fall under energy frontier, intensity frontier, and cosmic frontier. You will find that theory frontier is missing, but that is again mainly because theories actually come in all of these three things. Pure theory projects normally do not take a lot of money and don't come under mega science public. So the energy frontier, the main questions that were, so I'll come to that. Normally, I use the word normally. The main areas were identified as the following. Under energy frontier, we have Higgs properties, new physics searches, and future colliders. Under intensity frontier, we had flavor physics, neutrino physics, and precision measurements. Under cosmic frontier, we had dark matter searches, again neutrino physics, and study of cosmic rays. And it was realized that all of these three frontiers depend on two main pillars. One is the detector R&D. So this is the expertise that we have in building detectors. And second is high performance computation. So for actually executing this vision, you need both of these, which need to be invested in. So currently, for example, we have our major projects are CMS and BEL. ICAL at INO would have been, unfortunately, there's no underground site, and that's in deep freeze. But these are the two in which we have been contributing. You will see more in this report. And in astroparticle physics, what we have are not what typically are called as mega science projects. However, most of them have the potential of developing into big projects. So therefore, we call them as proto mega science projects. One of which is owned by TIFR, which is GRAPES 3 at UT. Then there is the MACE, the atmospheric Cherenkov experiment in Ladakh. BRC is the main contributor to this. In the Jadugoda mines, there is the experiment called JUSL or INDEX, which is for dark matter search. This is led by scientists from SINP. And right now, right here in TIFR, we have some development going on the neutrino reservoir beta decay. So all of these are potential to grow into big projects, but right now they are still at a proto level. So finally, this is what comes out as the top priority projects of high energy physics. So in the collider experiments, continuous support to the current high energy MSPs, which are CMS and BEL2. Planning and R&D efforts for experiments and future colliders like FCCE or FCCPP or muon collider. Now, which of these actually comes into existence doesn't depend on us. It's a decision taken by the bigger physics community as a whole, and where funding comes from. However, it was also decided that R&D for instrumentation for new technologies for future detectors, for example, quantum sensors, should be a priority, because it's not just participating in projects which are big now, but preparing for projects which will become good later, and therefore new technology instrumentation was a priority area. In underground experiments, it was strongly recommended that there should be continued efforts to establish an underground observatory, which will be useful for high energy physics, nuclear physics, and astrophysics. And in fact, recently people from the area of seismology and geophysics also have joined this effort. So although we did not succeed yet in finding a place for INO, we expect that these efforts will continue and we will get something, because that really opens up lots of opportunities. And we thought that the INDEX, which is the dark matter search experiment, could actually even serve as a flagship experiment, simply because dark matter happens to be an area which is in the limelight, so to say. Okay, doesn't mean others are not important, but this was just flagged as something which is already going on. In neutrino experiments, there is this deep underground neutrino experiment in the USA, in which currently lots of Indian institutions are already participating. And there is some possibility of building the important contribution component of a near detector. And this participation was recommended as a priority. In the cosmic ray experiments, we already have GRAPES 3 and MACE. There is also a neutrino scattering experiment which recently has started, which is called ICNSE, and that is to be continued. But in future, we are going to be looking at stereo MACE, which is two MACE telescopes, and looking also at synergy between them. Should be pursued very aggressively, and participation in the CTA, which is a Cherenkov Telescope Array Observatory, is recommended. It also has some synergy with the MACE, in which some of our colleagues are already involved in. So these were identified as the top priority areas in which combined concerted work should start and continue immediately. Then there are some forthcoming projects which are identified as potentially important projects. So for example, collider experiments like LHC are very big, But on top of that, there are riding experiments that have relatively less amount of funding and manpower is involved. One of them is Matusla, which is connected with CMS. It is next to CMS site, and some people are interested in doing this. And here we can work right from the R&D stage because it has yet to be set up. Other two experiments are neutrino experiments. One about neutrinos from a beam, and this is a special experiment which will be about cosmic neutrinos. So again, for both of them, a critical mass of the community doesn't exist now. And for them to become really mega scale science experiments, we need to have more number of people who say that we form a community and come forward and say we are interested. So that has not happened yet. That's the reason that these are not high priority projects. But one big category that people focused on are niche indigenous projects that we need to talk about. This JUSL, so this is Jadugoda Underground Science Laboratory. This is Indian dark matter search experiment. So these are this is already going on. I mentioned about Tintin, which is the neutrinoless double bitter experiment happening in on which some R&D is happening in TIFR. And another idea of observing low energy solar neutrinos using deuterated liquid scintillator called DLS is something on which some combined work is going on by people from TIFR and BRC. This is actually interesting because India happens to be the largest producer of heavy water in the world, and that's our advantage which we can actually. However, all these three experiments, if they really need to go to the stage of their full expansion, need an underground facility, and therefore what I mentioned earlier is actually important. Another experiment that has also started is called ISMIRAN. It's a reactor monitoring and sterile neutrino search experiment. It is started in BRC, and I think this is being taken to Kalpakam, if I'm correct, the detector, but I'm not very sure about this right now. And there was a possibility, this likely in the future, of satellite-based experiments exploring the universe in the medium energy gamma ray, so of the order of hundreds of keVs to 10 to 100 MeV. So, okay, so these are the things that we think need to be. I mentioned a lot of projects, but you have to also remember that everything doesn't happen simultaneously. So this is time scale from 2020 to 2035. These are ongoing projects, and you see green means data is being taken. But for all the future projects, the current stage has to be planning and R&D and commissioning. Data taking will start maybe in 2030 or afterwards. So every time that you are working on an experiment, for some experiments you take data and analyze it. For some experiments you spend time in planning and R&D of this. Okay, this was about high energy physics. But now I'll come to some common recommendations that are applicable to all the MSCs. So firstly, you can think of participation in MSPs as three levels. One is involvement of Indian scientists as users in major facilities, which is what happened long ago. We participated in CERN before LAP in various small experiments, D0 or CDF in Tevatron. We went to DAISY, 3S or KEK for doing experiments with synchrotron sources for material science and biology. The next stage where we are sort of on average currently is that we are involved in international programs and facilities. So we design detectors at Tevatron, LAP, LHC. We participated at LHC in making accelerator component, detector hardware, so on and so forth. But we perhaps would like to go to the next level where international community will participate in Indian facilities and experiments. And this part also helps us to build up some big science culture in India. And that was kept in mind. And this needs building infrastructure in the country. So this you cannot start at one go. And therefore, three things were identified as major directions to go if you want to build infrastructure. One is a National Detector Development and Training Center or a facility for high energy physics. This is the notation of nuclear physics document. This is the notation of high energy physics document, but finally what it means is exactly the same. Common facilities for developing detectors which can host state-of-the-art laboratories or workshop for instrumentation, testing and computation. And in fact, the idea is that sometimes very big instrument that you need to make something cannot be available at many places. No, not many universities can have this. One good place to combine them might actually be good. That it was mentioned specifically that researchers in universities can continue to carry out what they do locally at a small scale, but anything that happens at a large scale should be happening at this facility. I already mentioned to you about the underground laboratory. And third thing was training, outreach, and science communication about specialized advanced schools, centralized outreach unit, so on and so on. One important thing that we need for any kind of mega science is high performance computing that is across all streams. Some estimations were done about what kind of data centers we might need around the country, not just one but multiple ones, taking into account that the requirement is for many different quarters, including connectivity and user support and so on and so on. So one question was how to making of a mega science project simpler. One recommendation we had is that this is again people who know about line of budgets might know this, others may not, and then maybe I fall among the second category. The separate line in the budgets of funding agencies saying mega science, so that money comes from that and doesn't take it from people who do tabletop science. There's a common portal or a mega science coordination unit, which is a single window for communication between project proponents and funding agencies. Then we should also encourage feeder projects, which, as I mentioned earlier, do not reach level of MSP at the moment, but have the potential. And then one important part was initiation of new MSPs. So a clear path is set up in which you have to first have a community planning exercise, then communication with funding agencies through this mega science coordination unit, and the formation of a consultative group, which will help the science to proceed. Okay. So the way it finally will go is perhaps there is some portal, which is a common window, so that communication to funding agencies and to project proponents becomes easier. Okay. This is the final slide. Just to mention that although I talked mainly about high energy and Palit will talk about nuclear and Manoj about astronomy, astrophysics, the regions are not really completely independent. You see these topics which have dark matter. This is can be found by astrophysics as well as in particle physics. Neutrinos, for example, is an area which is common to the heart of both high energy physics people as well as nuclear physics people, because a lot of nuclear chemistry goes in the detection of neutrinos. This is, of course, gravitational wave. This is TMT. This is exploration of the interior of the sun. Again, something common to high energy physics as well as astronomy and astrophysics. And of course, there's a deep connection between nuclear physics and accelerator technology, so that the Pelletron LINAC at TIFR, at IUAC, cyclotron at VECC, and these kinds of RIB and ion facilities form a part of the whole. So finally, although vision documents are separate, I guess that a net vision should be somewhat end up being more unified. So I stop here and I will give Palit for the minister.
Also, you provided an overview of the whole process. Maybe we can take a couple of questions now and then then we throw it open for discussion after our turn. Govinda.
These slides, I have 2%. You have a few more. One more. Yeah, no, one more. This one, involvement of Indian science as a user. Is it written in the document? To my knowledge, L3 and D0, those was the most hardware intensive project is Indian people participate. This was not as a user. This was the detector was built in India and it was put there.
Okay. No, this part, this is only for my slide. This has not gone in this.
That's why I'm saying that. This was that to my knowledge, that the L3 time, this is the one of the NCAP detector completely made here.
Okay.
D0 time, this upgraded neon detector was completely made here. Not only made, it was completely designed. Readout, electronics, power supply, everything was developed here. So that was the most of this. So this is, that's why I'm surprised that it is written, no written.
Yeah, this I gave as an example, but okay, I can simply remove
So
this.
these are these
sir.
were the complete.
But it's only in my slides. It is not not in.
And
Thanks.
second point, I'm saying that, okay, this is in general, I'm saying that overall, I think last 20 years, and many times I said in the many forum, you show the big list of the things. That's fine, the wish list. Everybody want that 1% want for the 20 project. I think I was telling you, when this is the Dighe this project, this was that more than 10 faculty member work for one project. It succeed. Now the 10 faculty member, if you put this in the 100 project, it will be, everything will be in the background. Nothing will
Agreed.
So
I agree with you.
I'm saying that as a physicist or the individual people-wise, people may want that many things, but somebody from the top has to restrict it and forced to do something what people think in the best, not to divert all the.
Fair enough. I agree entirely.
But I think the document is very clear about, since these are mega projects, you can't do very many.
Yeah, no, I must also mention that when something is mentioned here, it only means there's a desire, and anybody who wants to make a project should also separately approach funding agencies.
Oh, I'm saying that somebody from the top has to instruct these people that you cannot go beyond this many. That has to be there.
Agreed.
Otherwise,
Yes, agreed.
Okay.
I have a request. I think since anyway, a lot of questions will be common, it's probably better that we have the presentations and then have the discussion. I think.
There's some margin questions on the process or anything. Maybe Sushil, I'll just take one more from Sushil and then we'll proceed.
Yeah, thanks, Manoj. So your title mentions 2035, the year 2035, but typically we talk about T0 plus certain years. So how many years did you envisage when these documents?
No, this year is still 2035. So say this, as I said, the writing of document took almost 3 to 4 years. Okay, so it was 10 to 15 years in future. All of these projects are up in the air, right? Without any time. So only when somebody concretely proposes a project, that's when T equal to 0 starts.
Okay, I think since these are policy matters, there will be a lot more discussion. So we will throw it open for discussion after the other two presentations. So we'll next have Rudrajyoti Palit talking about the nuclear physics mega science document.
Slide so.
So this is the front page and the back side of this document. And this was something which was prepared as a part of this mega science activity. So as you can see that this document will have three major, is based on three major parts. One is the QCD physics. The another one is accelerator based and non-accelerator based low energy nuclear physics. The other one is the plasma physics. So, and then it also talks about all the other components or the subtopics of say accelerator based nuclear physics, and then the fundamental symmetries and neutrino physics and dark matter. And there are also implications in the accelerator, medical applications and detectors. So these are something which all the aspects of these topics are covered and discussed in the document. So the document tries to answer, address the questions related to nuclear physics in different energy and length scales. So these are the different and addresses the questions about the mega science project of basic research in nuclear physics, as well as in the nuclear energy, which is the plasma physics part. So the type of questions in low energy nuclear physics which one asks is what are the limits of existence and what are the different type of structure of nuclei that exist, and where in the universe and how the heavy elements are formed. So these are the questions which people are asking from these experiments. The another part is the QCD phase diagram, which is the relativistic heavy ion collision experiment. The other one is the plasma physics experiment related with the nuclear energy. So I'll be talking about the experimental facilities within India and outside. This document gives an exhaustive list of all the facilities. I'll talk about the overview of nuclear structure and reactions activity in India. Then I'll talk about the recommendations from these three topics. So this is the IPAC report of the, here you can see the pink points here are the different nuclear physics facilities from starting from Australia, Japan, China, and India, Europe, North America, and in South America. You can see there, and then in Africa, there are a lot of facilities which are there. And this is a field which is growing because of technological development. And these are the facilities within India. These are the similar facilities between TIFR, this TIFR VRC accelerator facility here. We have a similar facility at IUS in New Delhi. This is a university-based center. Then at SINP, there is a new accelerator. VCC, there are many accelerators, cyclotron accelerator. And in VRC, they have reactors as well as accelerators, high current proton accelerators, which is present. Nuclear physics experiments, low energy nuclear physics experiment traditionally have been going on with a group of 5 to 10 people. But over the year, because of the complexity and because of the large resources required, I've given you two examples here. This is a scattering chamber where you have sophisticated silicon detectors, large number of silicon detectors. And typically this type of experiments, you have about 10 to 15 people now. And many people come here and propose experiment and they perform the experiment here. And now, because of the complexity of another class of experiment, which is the Indian National Gamma Array, because of the complexity and huge resources required, this is some collaboration which is it's not at the level of ALICE or CMS. Nevertheless, we have about 70 people, which is quite a lot. And in a typical experimental paper, you will find out that about 20 to 30 people are involved. So that is the scale of involvement of the different groups. So while the mega science vision document was prepared, this was another accelerator facility which was proposed that this is something from the Dighe, like now it is almost approved. In last couple of years, we see that this facility, which can give radioactive ion beam as well as stable beam from proton to uranium, this facility in principle is approved, and the R&D is going on in VRC, and this will come up at Vizag. So I have just to give you a flavor of the nuclear physics, low energy nuclear physics. So we talk of the cell model, we talk of the collective model. Another part is the clusters. So there is a lot of activity which is going on. So people know about beryllium-8, which is 2 alpha. Some experiments were done here. Then people talk of Hall states, halo structure, strength, molecular structure in nucleus. So one of the question is, can one find out neutron droplets? So this is one experiment which was done. This is an effort which is going on for last 40 years. And very recently in Riken, this experiment was done, and using invariant mass method, they have identified a resonance in this 4 neutron. And this is something which is identified, but the direct detection of this tetraneutron has not been done. And interestingly, while talking with our colleagues from DTP, we find out that they are also interested and they're working on lattice calculations, Nilmani and his group, to find out the properties of tetraneutron from lattice QCD. So the question is trying to understand from neutron droplets to neutron star, trying to understand the neutron skin. So all these topics are related, and accelerator-based nuclear physics is going to play a key role in understanding the evolution of the neutron droplets to neutron star through the neutron skin. And for this, Indian groups, we have these facilities within India, and hopefully in next 10 years' time, we'll have this future accelerator facility in Vizag operational. And Indian government has given funds for participation in the New Star. India is at FAIR, and India is a partner in this making the accelerator for the FAIR facility. And there is a lot of scope and opportunities for low energy nuclear physics community, which is about 250 researchers within the country. And there are about many universities and institutes across India who are involved in this type of activity. Yeah. So this is an overview of the FAIR facility. It's a India-FAIR collaboration which was formed some time back, and Government of India has signed agreement with Germany, and India is giving about 60 million euro for this facility, and not only making the accelerator, but also in certain experiments, low energy experiments, India is contributing, as well as in the CBM experiment, India is a big partner. And one of the key features of this facility is that we can get very high energy beams of 1 to 2 GeV per nucleon. And that gives the unique opportunity that the identification of very heavy elements will be clearly done, and this will be really competitive. And this is the unique feature of this facility, where you can identify the very heavy elements in mass 200 region. You can identify these isotopes very cleanly because of the high energy. And what type of questions which you can ask, as you can see here, this is the type of isotopes intensity you can produce. Some of the these are the black ones, are the stable isotopes. And as you go out of away from the line of stability, the production cross section goes down, and you have isotopes which is like 1 ion per second, and you need to make state-of-the-art detectors to even if one isotope per day is produced, you will be able to measure that properties. So what are the questions which you are trying to ask? You will try to talk about the halo nucleus, you will talk about neutron skin, and neutron skin is related with something called the Pigby resonance, where the skin neutrons are oscillating against the core, and that is related to the equation of state of nuclear matter, which can give properties of the neutron stars. And combining the nuclear physics experiment with precision astronomy, you can constrain the astrophysical scenario. So that is one of the key aspect of the experiments. So these are the broad questions in nuclear physics. I'll not go through all of them. So one of the things is that we want to understand how did visible matter come into the universe, and how the matter organize itself, and different low energy phenomena they emerge. Like one of the other question is the elemental abundance of particularly for the heavier elements. You want to understand the nuclear fission process in a very microscopic way, and there are many new controlled experiments for which you can do it. If one wants to do the nuclear astrophysics at low energy, high current facility and try to understand the formation of elements in the stars. There is another aspect is the neutrino-less double beta decay. And here, apart from measurement of the experimental signal of neutrino-less double beta decay using bolometers, you also need nuclear structure information, and for which you need accelerator-based experiment. And you also, from these properties, you can also try to find out many aspects of the nuclear-nucleon interaction. So this is the recommendation of the one part, that there is the first recommendation is to make new accelerator facilities within India for radioactive ion beams, make underground facilities for low energy nuclear physics experiments, then strong participation in FAIR and other international facilities for RIB and photon beams, state-of-the-art detector systems for INGA or any other spectrometer at the existing accelerator facilities, and a consortium will be formed to facilitate the usage of provide ecosystem to the low energy physics community to participate in international experiments. So this is the high energy nuclear physics the document, the physics part of the high energy nuclear physics. So one of the main thing is to find out what is the phase diagram of the QCD. So this is something for which the existing experiments, they are working on the ALICE as well as the RIC. And in future, when the CBM will be available at FAIR, then there will be experiments and the community will participate in this experiment, and they are also proposing experiments at EIC. So these are the recommendation for the QCD physics. So continuing participation in heavy ion programs at LHC, RIC and FAIR, and the collision energies of which only to map the QCD phase diagram. Then the CBM experiment, which is under construction. India is contributing in the muon detectors for this, and participation in upcoming electron ion collider experiment to address fundamental questions in nuclear physics. So this is the plasma physics. These are the three broad questions. So one of the things is how to understand astroplasma using multi-scale collision-less reconnections. And here the Plasma Research Institute, they are taking the lead, and they are also involved at different international projects like ITERs and the tokamaks. So these are the recommendations. So one of the recommendations is to build a moderate size spherical tokamak that can be used for the production of radioactive sources for medical purpose, production of tritium for conventional fusion reactors, or core of fission fusion hybrid reactor. And they are also setting up, the recommendation is for setting up high energy, high power pulsed facility for producing intense plasma. So as Amol has already mentioned, one of the, for all these experiments, one of the main part is a training and as well as a detector development center. And these are the different detectors which are, the activities are going on with semiconductor detector, inorganic scintillators. Interestingly, you'll find out that colleagues from TIFR Hyderabad and TIFR DCMP, they are interested in growth of certain radiation detectors, which will play like big role in the R&D activities. And one of the aspect is to have the instrumentation development center, which will be also part of the training for the students for coming from the different institutes and universities. So the document also talks about science beyond basic science. So the accelerators can be used for radiation hard material testings, agriculture, reactor monitoring, nuclear waste management, and some of the colleagues from here in chemistry, they are interested to have heavy ion beams from palladium or some of these isotopes. So in the future facilities, maybe it will be possible, and that will be useful for the environmental science. Another aspect is the development of detector that can really make breakthroughs in the medical imaging aspect, which are discussed in this document. And this is the last one. So another part of the document says that how the industry, Indian industry, are participating and contributing in the mega science projects. And these are the list of components which already Indian industries have contributed to different mega science projects. So this is the summary of the three parts which I have already discussed, and lack of time I am not reading again, but this is the summary of the three parts. And yeah, so this is the working group and who have contributed for this document. Thank you.
I'll try to be quick. So this is the Mega Science Vision Document 2035 for astronomy and astrophysics. As Amol mentioned, exercise led by the PSA's office, and these are sort of my summary of what it emphasizes. Leadership in key frontiers, building technology and human capacity, and long-term participation in international mega projects. I will have a final summary later. Amol said for many of these disciplines, this was the first time such an exercise was undertaken. But for astronomy, it was different. There was a vision exercise in 2004 by Indian Academy of Sciences, Bangalore. And what was really reassuring is that most of the recommendations from that vision document are now realized. AstroSat was, as a high priority in that. The niche that vision document, particular vision document, stress was the multi-wavelength approach. AstroSat was one of them. That's now done. A 4-meter class telescope, DOT, that has come up. Wideband capable of GMRT. Now the UGMRT is available for users. Participation in large international telescope project, which has been realized by our Indian participation in SK and TMT. There was a specific recommendation on space-based solar chronograph. Aditya L1 is up there. And an imaging TeV gamma ray telescope, MACE, is up. So a good number of the recommendations were realized. Now, this document starts with a bunch of science questions, and it's kind of essentially the question of origin. How did the universe begin? How do galaxies form and evolve? How do stars form in galaxies, and then planetary systems form? And finally, how life happens on planets. So I'll not dwell much on the science questions. And the next thing the document does is take stock of India's current landscape and highlight that India already has a strong multi-wavelength foundation in terms of observational facilities. Not just multi-wavelength, multi-messenger, I must say. Cosmic rays, Graves 3, we heard a lot about it in the morning meeting. Gamma rays, Tactic, Hagar, now MACE. X-rays and UV astrosat in space. In visual, near-infrared, and radio, these are the observatories spread all across India. GMRT, Gauri Bidnu Radio Telescope, and ORT. And for radio, visual, near-infrared, HCT on Hanley, DOT at Devastal, Nainital, the Sambhunananda Telescope, IGO at Giravali, Mount Abu Telescope of PRL. USO is a solar telescope, and VBO, the Vainu Observatory. And then Kodaikanal Observatory. These two are solar observatories, USO and Kodaikanal Observatory. And of course, the TIFR balloon facility, which specializes, which has this unique niche in far infrared observations. And that's a TIFR instrument. Swarna is here. Glad to see him. Yeah. See, I just wanted to, so despite of all this, India still lags behind, despite this foundation in multi-wavelength observing facilities. India is far behind when compared to the world facilities, existing facilities in the world. Here I try to trace a chronological summary of the optical IR telescopes in India, and this is more or less applies to other wavelengths as well. Before 1960, we didn't have any professional optical IR telescope, whereas around the world, you already had 100-inch Mount Wilson and 200-inch Palomar already. But in between this period, Vainu Bapu, the father of optical astronomy in India, he came back to India, and late 60s, he had already ordered two 1-meter class telescopes from Carl Zeiss, one in Nainital and the other went to Kavalur, and they were up by 71, 72. Around the world, it still was 3 to 4 meter class telescope. The gap was not very large, but soon after he installed this, Bapu had already planned for a 2.34 meter telescope. And again, roughly around that time, it was, so it finally realized in 1986, the VBT, Vainu Bapu telescope, when at that time, and for many years, it was the largest telescope in Asia, optical IR telescope in Asia. Again, the world was, 4 to 6 meter class. That 6 meter was a Russian telescope, which never really functioned. And Hubble's telescope would be launched in 1990. But then the gap, the ground-based astronomy, that gap wasn't that great. But then from 1990 to 2025, we are still stuck with 2 to 3 meter, 4 meter class telescope, whereas the world has leapfrogged to 8 to 10 meter class telescope. And now they're talking about 30 meter class telescope. See, the aperture, the size of the primary aperture is very important for astronomy. That tells you how much light you can collect, so how faint you can go. So in astronomy, there is this concept of look back time. The deeper you look, you're looking back in time. If you want to study the young universe, you really need to collect light. You really need large apertures. So the larger the aperture, closer to the frontier questions you are. So this was recognized by the vision document, and or even earlier that, and India has already joined. These are some of the international mega projects India are already part of. TMT, SKA, and LIGO India. TMT and SKA, the funding is approved, and LIGO India, it's still hopefully it will be approved soon. And India is also part of. There is Indian contribution to some of these international projects. Rubin Observatory, Indian astronomers have data access. CTAO, the phase 1, there was TIFR, VRC, SINP were part of it. Now they are planning to restart the negotiation to become the phase, part of CTAO. Then there is this Mauna Kea Spectroscopic Explorer. This is kind of refurbished CFHT, the Canadian-French Hawaii telescope, for a large spectroscopic survey. IAA is an associate member. So here we are, sort of a member or, a small part of the thing. So these big international mega projects are timelines. So what I want you to notice particularly our share here, TMT, it's 10%, SKA, 6-7%. LIGO, if realized, it will be entirely ours. CTA, I guess it's 5 to 10%, and MSc similar. But the timescales are 10 to 15 years. So there was a question by Sushil. T0 plus 15 years, Sushil, roughly. But that's too optimistic, if you ask me. It can easily spill over to 2040. These are huge projects. And TMT is in a slightly fluid situation because partly because of site issue and also now Trump's serious cut to NSF. So the TMT was expecting a 20%, NSF as a 20% partner. So that's not going to happen, or at least not in the near future. So, but then the Europeans have come in. Spain has given promised $400 million. European Central Bank is offering a $1 billion credit so this might actually become US might be out of it. That's a possibility. So our funding agency will make a decision early next year. That's what I'm hearing. So SK, in 2-3 years, we'll see the first light, and so that's a smooth path. Now the recommendations of the national mega project science, the highest priority was NLOT, was called the National Large Optical IR Telescope, a large aperture, 10 to 12 meter class optical IR telescope at the Hanley site. And also National Large Solar Telescope, a 2 meter class solar telescope to study the sun. That's again in Ladakh. It's near Pangong Lake, somewhere in that area. The other recommendation, highest priority recommendation, Himalayan submillimeter facility. What's recommended is a 15-meter class submillimeter telescope. See, submillimeter in the entire electromagnetic spectrum, if you take the pan TIFR expertise, one gaping hole is this wavelength range or the frequency range, the terahertz to. So basically 300 microns to 1 millimeter. And we already are making headway into that. The satellites application center, SAC ISRO, is building a 6-meter submillimeter dish. So we are building receivers for it. Bashwati Mukherjee is leading this effort. So we are in talks with them, and they want to. So ISRO wants to install it at Hanley. Hanley, because that's where the water vapor. See, for submillimeter, the water vapor in the atmosphere is a big issue. So you need to have a dry site, and Hanley fits the bill. The idea is to sort of go to a 15-meter submillimeter telescope soon. So gamma ray, ground-based gamma ray is very interesting. It finds mention in both high energy physics vision document and astronomy vision document. And the same thing, the MACE-2, I mean, the future mission MACE-2 and CTA participation. And they also mentioned this, I believe, is a slightly more long-term thing, the Schwarzschild Koda telescope, SCT array. So these three are the highest priority national mega projects in astro. The NLOT, the Large Optical IR Telescope, the Large Solar Telescope, submillimeter facility at high altitude, Himalayas, and ground-based gamma ray astronomy. And timeline, again, because this document is a vision document for 2035, it's kind of all around that time, but they all will easily go beyond that. The priorities are very clear in the optical IR wavelengths, TMT and NLOT, undoubtedly, and SK in radio SK, submillimeter terahertz, the 15-meter sub telescope. So we're just beginning with the 6-meter thing and building receivers for it. Gamma ray, MACE-2, participation in CTAO, and gravitational wave LIGO. So these are the highest priority facilities, international and national facilities that the vision document is strongly recommending. And to sort of sustain and create an ecosystem and sustain these activities, some of these smaller projects, like Amol said, feeder projects or whatever, they are recommended. Participation in international, already existing 8 to 10 meter class observatories. Sandeep will know we did make an effort in that direction. Then just because we go for large aperture telescope, it doesn't mean that we close down all the small aperture telescopes. So we should have a network of small telescope for sort of training the students and also carrying out some niche projects. EGMRT finds a mention, and these two aspects are stressed as the highest priority: the capacity building, technology and human resource development, and computational requirements. So these two aspects are common in other vision document as well. There's also mention of some of the space missions. ExoWorld and IRSIS are of interest to TIFR. ISRO is somewhat slow on this, so but things are as far as ExoWorld is concerned, I'm hearing that things are moving. So DAA has strong interest in that. 4 of us are part of it. Computing facilities. So this is very similar to what has been found in the other vision documents, but very specific, astro-specific aims. Computing center for space weather forecasting, square kilometer array data and analysis, etc. Gravitational wave data analysis and numerical relativity and general computational astrophysics, and for other mega projects. So the recommendation is to start with, so it kind of exhorts astronomers or astrophysicists to come together and put in a proposal as part of a national supercomputing mission. I think some movement in that direction is already happening in the community. The astro community has been growing. This is a demographic breakdown for our professional bodies annual meeting in 2023. That's Astronomical Society of India. Yeah, so 50% PhD students in this age range. So that's quite reassuring. And both publication and impact have been growing significantly. So the community is growing. And so also synergy with other research areas, laboratory astrophysics, astrochemistry, astrobiology, nuclear physics, something that we have in common with DNAP, the nuclear physics document, and also enhanced technologies, data analytics, big data, AI, ML, all these fine mentions. I'll skip this. And finally, to summarize, the 4 main themes: access to world-class facilities, development of national facilities, data and computing infrastructure, human and technological capacity building. So this is sort of, in a nutshell, what the Astrovision document is telling us. So that takes us to the end of this. So before I throw it open for discussion, may I ask Sandeep to say a few words? He constituted some of these committees during his time as director. So Sandeep.
Won't take up time, but thank you, Manoj. What I really want to do, thank you, is I want to thank a few people. Jairam is not here. I'm sure he's very busy, but I was involved, in at least 2 of the vision documents for nuclear physics and high energy physics, because TIFR was made the nodal institution. And of course, we were also involved in the astronomy. So I want to say that some of TIFR faculty have worked tirelessly in bringing these vision documents out, and I want to thank them. Amol really played an absolutely key role as the convener in both the high energy physics and nuclear physics documents. I know every Saturday there would be meetings, and with his thoroughness, patience, it wouldn't have happened. Thank you. Palit was the convener in nuclear physics, was a key person in the nuclear physics, so we really have to thank him. Shrirup, also as a working group member in the high energy physics. Then there are many more people. Vandana is sitting here. Thank you very much for being part of the nuclear physics working group. Kajori is here. Yes, Kajori, thank you for joining today, and thank you for being part of the working group in high energy physics. And okay, I didn't know that. I'm so sorry. Please excuse me, Pravarta. Thank you also very much for being that. Yes, I'm coming to that. And I wanted to say, coming to nuclear physics, Yashwant and Devendra, I don't know if Devendra is here, but thank you. In Astro, what did I say? Astro, yes. Devendra and Yashwant, and of course Manoj. And now I might have forgotten someone, so then please excuse me. But there's one more person I really want to thank, okay, without whom this would not have happened, and he is Praveer Asthana. And Praveer Asthana was the nodal person in the Principal Scientific Advisor's office. He's a person with great feeling and regard for TIFR, and I really, without his help, he was pivotal in setting up this structure that we also used, conveners, working groups, and also thank him also. And last thing I want to say, then I'll get off the mic, is this, a lot of work has gone into these documents, but actually, let me say, it's only the first step, okay? And I urge you all especially the younger people, to take this forward and come up with a few concrete, distill it further, come up with a few concrete projects, and then interface with the government so that there's a glorious future in these wonderful subjects. And TIFR has to play a key role to bring that about. So I think special request to all of you gathered here. Thank you.
Thank you, Sandeep. Let's have discussion, questions, comments, suggestions, Sandeep.
Thank you, Sandeep, for the kind words.
Sandeep.
Yeah, I guess these are very nice, ambitious projects. So my question is, do we have a rough estimate of the budgets for these things so that a policymaker would want to know this? It's in the book. Nice.
Yeah, some zero estimate. But I think the idea is for now a group of people to take it forward and convert it into a DPR and just take it. Idea of order of magnitude we will get. Yeah. Subdeep.
Maybe just a quick comment for others to get clarified that LIGO India is now funded like almost 2.5 years back with full funding from both DST and DAE. So it's ongoing yeah, it's already approved 2.5 years back. Yeah.
Sorry.
Yeah. So.
I wanted to make a couple of comments. I think one thing I want to point out is that, of course, I mean, what Sanju said, the committees, when they were made, one of the really a major point which noticed I was, apart from subject expertise, the committees actually had all the mega science documents, maintained a good diversity. And I think the documents have also given some recommendations for that. And that's one aspect the human resource development has to really take it forward. The second comment I want to make is, of course, it's really a great credit to TIFR that TIFR was given this role, which is there, and in spite of the dwindling numbers, so that something which we need to come back to the numbers. So one point I just wanted to add there is, at least in these areas, often we feel that, our own students are back into the system and not all the other institutes do that. So this discussion comes up in the institute. So here I want to emphasize that the kind of training and the kind of overall growth and the contribution to the big projects, the training our students get here, actually, it's almost unparalleled. So it's inevitable that we will be getting it back. I mean, we cannot not take them back to make things forward.
The question, Acharya.
Sure. In the astrophysics part, it looks like neutrino astronomy has been left out. There is no mention of that. At least you did not mention about that. But okay. But it is covered partly in the high energy physics. Anyway, yeah. I was just wondering.
Yeah. There was sort of.
Yeah, so since this point about taking our own students have come up, I want to make a comment that it's always it's good to take the best students probably who have gone out of TIFR. But if we are not getting applications on a field from internationally established places, then we also should look at the possibility that maybe it's no longer a project which needs to be continued. So there should be a very, very detailed discussion on whether such a project it should not be that a project has started, it should continue, and therefore we need a person who is a TIFR graduate. I just wanted to make that comment.
Any other comments? Questions? Suggestions after having listened to all this? How should we move forward? Gagan? Yeah. Yeah.
Yeah, so I think this point that Vandana made, and also the thing which has been suggested on this instrumentation center. So one of the key thing for this mega science thing is building the instrument. and TIFR was known or is known or will be known if we want to continue that. So I think some concrete thing, if we can to take up this instrumentation center and this human resource development, they will be the feeder for the next generation mega science, right? So of course, in the mega science, one can argue where we should focus, how we should, but important thing is your foot soldier, they have to be there, right? So therefore, so if I have to say that this instrumentation center and human resource development is something we should really think of, and some niche experimental thing.
In the nuclear physics and the high energy physics vision document, the centralized instrumentation facility sort of thing is mentioned. But in Astro document also there was the suggestion, but they don't further develop it. So it's kind of one of the directive principle to do it, but no more details. Oh,
So what I was asking was, have there been any discussions on having international contributions in Indian projects? Because the other way around is something that's heavily discussed, but what about the other way around?
This has happened. For example, GMRT is a very good example. We build GMRT, and the time on GMRT is taken by, I don't know what percent, but I think more than 70% people are actually, is actually tested.
It's highly,
right? So you should have your own experiment working here first. I know was this idea. If you had built that, it would have had international. So you should have something which is based in India for doing something, and then people will join. That was.
Yeah, regarding the international participation in domestic experiments, it's been there for I think for last 6-7 decades. Some of the right from the KGF to GREPS 3, at CRL, we have this participation, and recently there is a great interest from from USA and some other countries to participate. For example, on GREPS and these things. Yeah.
Before we, just give me a minute. Before we take further questions, I just wanted to tell you that we had a day-long discussion this morning about these various vision documents and the mega science projects that were discussed, trying to see how TIFR could lead one or few of them. And tomorrow morning, 10 to 12, we will be summarizing our today's discussion, and director and dean have agreed to be there, so you're welcome to attend the session.
So you mentioned two projects, but you didn't really discuss too much. But maybe, at least for some of us, it's still of quite interest. One is EGMRT. The other is NLOT. Now, given the fact that certain projects are international projects are in flux, like you mentioned TMT, and there are other projects also which may be in flux because of funding cuts. So is there any kind of a vision to sort of utilize these opportunities? So, two questions. One is specifically towards two projects, astronomy projects, and other is.
I don't know, but I can, and even EGMRT, I don't know the details. I mean, the proposal has been there for a while, and people have taken it up, and and are pushing ahead with it. But NLOT, I can comment on. There's already a lot of movement on the ground. In about November 2023, a national kind of core team was formed with directors of various institutes and universities recommending one representative to that team. And we have been holding discussions for the last 2 years or so, on and off. And now there is some, after the TMT thing, the funding situation in the US, it has gained, so there's some impetus, and then we are pushing forward with the 10 to 12 meter class telescope. And we are getting very positive signals from funding agencies. DST is what we have been interacting with. So the off the record, recently Finance Minister visited Hanley, and she in fact, huh? Oh, okay. So maybe not. So there is movement on that front, and we are now working on a DPR for an LOT, and DST is asking us to go for the largest aperture, if possible, the largest aperture possible. So we are working for a 13.7 meter telescope. The advantages are a few. In the northern hemisphere, there is a Chinese telescope planned for 14 meter aperture telescope planned. We don't have much details. Notwithstanding that, this will be the largest telescope in the northern hemisphere if TMT doesn't materialize. So we are working towards that, but still in the early phase, we are working on a DPR, the design and other things. So we had some discussion in the morning today. So tomorrow we'll have some summary. So there'll be more details there if you want. But EGMRT also, yeah, things are happening. But as a coherent plan, I don't know if there is any such plan in astro or in other fields to take advantage of the current global situation.
For example, the funding that was already ascribed to TMT, India, can that be utilized somehow for the
So
NLL?
what I'm told is that the funding agencies will take a call early next year about the TMT participation. That's what. Yeah, so there's tea and snacks in West Canteen, outside the West Canteen terrace. So please have them. So any other questions? If not, let us thank the speakers.
Thanks, Manoj, for organizing this.